This is Byron Johnson. I'm with Coordinated Power, just giving you a quick walkthrough of what a typical grounding study might look like. For this example, we'll use WinIGS, but there's lots of softwares and lots of ways to do it. Here's just kind of the basic run through of what that looks like. So if you've seen the previous few videos of an introduction of what is touch and step voltage and ground potential rise, this will be a good follow-up to those. So WinIGS has a one-line editor. Now we can get a lot more advanced where we actually model the incoming transmission lines and generators, and a lot more stuff. But to keep it simple, we got just a current source here. So we got to be in the edit mode. We got a current source. You can see it's drawn a little bit funny on the one line, but you see it's broken out into a new bus A and a new bus neutral down here. We've set it to a current source. It's 10 kA current source. So let's say that represents the fault current that you were provided by the utility. So this ground impedance model, we connect to the neutral of it. And again, this one line here has it condensed, but this goes to the neutral of it. And here we have a little switch over that breaks out the phase A conductor and takes it over to the grid. You can see by clicking these nodes right here, the grounding system is connected to this connector that's connected to the A phase. Only because we named this the A phase on the current source. Right, so we named it that. We could have named it B, C, or something arbitrary. So that's how we got it hooked up. It's the current is flowing from the source through the switch to this ground mat, into the earth, then back out of the earth, and into this as the return. So a lot of times we'll make this, well, it doesn't matter if it's current source. Let's say it's a 1 ohm return grid. So just for reference, if you're building this yourself, the one line is an NMF file in WinIGS. You can create new ones by going to here, create a new one, or open one. These are where you insert the elements on the one line. The ground mat is under this one as a multi-terminal device. We got the connector from this one, and then the shunt devices was the current source, three-phase source. And again, you can model the transformer. You can model your actual, a source impedance with transmission line and distribution lines modeled. It's got a pretty rich interface for modeling those and getting all the accurate parameters that you would want to model. All right, so once we've got that set up, we'll go over to the Analysis tab. We will run the analysis. It solves the grounding mat system of equations and the current flows and all that. Then we're going to come over here and just real quick, I'll show you the graphical. You can see that the ground mat has 10 kA flowing in it and 10 kA going out here to remote earth. Then this resistor return has the 10 kA coming in and 10 kA on both sides. And you can see there's 10 kV across this return path. So that would be the GPR back at the return back to the source, where all of that current gets sucked up through the 1 ohm resistance to earth. And again, this isn't a 1 ohm resistor. This is a 1 ohm equivalent resistance from remote earth to the point where it comes out of the earth. So think back to the dirt resistors that we had built in one of the previous videos. So to view actually in the grid, we're going to go to grounding reports here on the reports tab. Then we're going to click into the grid. I'll make this bigger. One thing when you're designing the grid itself, we'll come back to that. You're going to input your soil resistivity parameters. So it actually already solved for these, and it made a 2-layer model with 478 ohm meters upper and 260 lower ohm meters, right? So the first layer has a thickness of 13 feet. And then the bottom layer is assumed to extend to infinity. That's just the 2-layer soil model for grounding. So you can see here, it's already solved this. So our grid resistance from the grid, and any point connected to the grid, right? The grid's all low impedance to itself. But to remote earth, right? So the part out there in our previous video where we had the shells, once the shells no longer matter and your current is fully dispersed into the earth, It's 5 ohms to get there from the grid to remote Earth, however far away that is. All right, so when you inject 10 kA into 5 ohms, then your grid goes to 58 kV. And this voltage here is the GPR. It's the voltage that the grid goes to with respect to remote Earth. And note, when you're doing a study like this, if you're injecting current, always be aware of your system voltage, right? So if this was a 34.5 kV high side, or even a 69 kV high side, there's no way that you're going to get this, because the maximum you could ever have here for your GPR would be your full phase to ground voltage, right? So on a 3-phase system, you've got a phase to neutral voltage. Your GPR can't ever be higher than that. That's the upper limit. So the GPR will always be, upper bound by the phase to neutral voltage of your system. So keep an eye on that. You don't want a system where your GPR is proposed higher than the system voltage could even make it if the full phase to ground system voltage was applied to your grid. All right, your resistive layer effects, that's where we put in the surface layer. So we'll put in the thickness. We like to go 3 to 6 inches. I'm not sure what that is in meters. Maybe that's right. And then we got 2,500 ohm meters. 8,000 is a good number out of the IEEE standard, but I've personally seen measurements done on that number 57 wash tone. And when it's wet, it's tricky to measure and feel good like you got a realistic measurement of it. But I've seen it lower, like 2,500s, and that's the reason why I like to use that lower number, just to be a little bit more conservative. So we're going to go over here to your allowables, right? And this is where we're going to enter our time for how long does that shock duration last. So let's say the utility told us, we got, or our source impedance calculations told us we got 10 kA ground fault current. Then how long before the relay trips and then the 3 to 5 cycle breaker actually opens. So we'll put that in there. You can even do this to see, what amounts are, body current versus shock duration is the title of the chart. We do it for a 50 kilogram person. You got a lot of options here. And it'll compute, because it already knows the soil resistivity, and it does that shock electrocution circuit calculations itself. And we're going to evaluate touch potential over the surface layer, which is the rock. And for the step potential, we're going to always want to change that to evaluate it over native soil, because the problems for step usually happen when you're stepping off the grid. So when right when you're leaving the grid, the dirt just outside the grid where there's conductor typically seems to be the steepest drop off in that potential, which you're subjected to in step potential cases. All right, so we got all that set. So then you come over here and you're going to run. First, we'll look at earth voltage. And I drew a big box out here for this. To put these boxes, you come over here and get that from the Insert 3D plot frame. And then when you click on the plot frame, you get a lot of options. Which type of calculation is it relevant to? Earth voltage only, touch, step. And another key thing here is you can draw a contour at something, right? So for earth voltage, it'll draw a contour for where it crosses the 300 volt line. And we won't see it in this plot because 10K is a high number and we got a high resistivity here, and it's just going to be a massive GPR event we're looking at here. For 58 kV, we already saw it. But for your touch and step plot voltages, it's also very good if you can get the permissible values and put them in here so you can see a contour of where the permissible is reached. And even better if you want to reduce that by 10% to give yourself 10% margin. So basically, if you get the yellow line somewhere, then you know that you're above that 10% margin to your allowable amount. So anyway, all right, we're going to run it. And this is the solution of it, right? You don't see the orange line anywhere, but you can see the other ones. You can see this blue line. You've dropped to about 5.7 kV. Here in the middle in the red, you're up more at the 46 kV. And then you can even look. I have to zoom way out. And that's what it looks like, right? So this is the GPR event, and the peaks are where the grid is. And then the drop-offs are where the dirt starts to fall away. And you can see as you move away from the grid where the current's injected, the voltage does start to drop and fall and fall and fall. And then over here where it's flat, that's your remote earth. So that's what that comes out to. We're going to come over here and run it again for touch voltage. And it typically looks like this, where you see the contours as concentric circles inside the mesh. And that's because, again, right at the conductor, everything is at the full GPR, but then the dirt starts to fall off away from that as you move away from the conductor. One way that I kind of like to think about it when I'm doing these models is that the conductor kind of taps the dirt. It taps it up to equipotentialize it. So if you had a whole, like just a copper plate across your whole substation, everywhere would be safe to stand and touch because it's all at that same potential. So, you know, if everything's at 58 kV and you're standing at 58 kV, then everything's safe. The problem just occurs when, you know, the dirt starts falling off in potential as you move away from it. So, two ways we can make this safe. One is to equipotentialize the whole thing. Yeah, but that's not cost effective. So the other is to sufficiently tap the dirt, right? So over here in the center where it's dropped off a lot, you could put another horizontal conductor across here and it'll bring all that dirt back up to GPR. And then you come over here and you split it this way and you put in, you know, horizontal and vertical conductors here until you have tapped it up to where the middle no longer exceeds the safe limit. Right, so imagine you're standing out here, somewhere in the middle, and you know you can touch something. If you can touch anything grounded here, you're going to be subjected to the difference between the dirt that you're standing on here and the rest of the grid voltage. And here we'll look at a 3D plot of this, if we can find it. There it is. You can see the touch voltage is the highest. And again, this is a plot of the difference. So every point on the plot is the difference between the potential at that location and the rest of the grid. And I think you can even see it as if this plane, oh, it's not going to adjust up to there. Well, I was going to put this plane up here at the GPR level, and you can see that it falls, you know, that it falls away. Or it actually, let's see, turn that back off. The touch voltage is actually the difference. So it's the highest on the dirt away from the conductors. But so you're going to want to make sure these peaks don't exceed the allowable. And you're going to do that across the whole substation. Also notice that we've got the fence modeled in here as well, so it counts as ground rods. And that was another thing to talk about is the ground rods. Where do you put ground rods and how do they help? When you put the horizontal conductors in, they're all, you know, 2.5 feet below the surface, and they help to equipotentialize all the dirt. Ground rods reach deeper down into the earth and effectively disperse current lower down deep into it where it doesn't have to go through as much earth. And effectively what it does is it fights the problem in a different way, where it lowers the resistance to earth and therefore lowers the GPR, right? So if you make that, back in our first video where we had the resistor that was representing resistance to remote earth, if you minimize that resistance, then your GPR gets lower. And effectively all your step voltage, touch voltage, and earth voltages, everything goes down. So again, the way I like to think about it is put horizontal and grid conductors in here to better equipotentialize the soil, and then put ground rods in to tap deeper into the earth and bring the overall GPR event down. Okay, and you can see here's the permissible. You're allowed to have 887 volts open circuit voltage on top of the rock layer, and our max by this point right here in the middle is 24 kV, so this is nowhere near safe. Then step voltage, we'll run this one as well, put a slightly bigger plot frame on this one, and you can see it starts to drop off. And you see right here, there's the maximums right when you leave the grid. So think about it, you're walking down that big waterfall looking GPR event that we were looking at earlier. And here's what the step voltage looks like. So if you've got a foot here and then the next foot is a little bit over from there, the steepest drop off is right at the edge of the grid. And it's much less of a problem inside the grid. So we'll go ahead and stop it there for just the basic modeling in WinIGS and pick up on the next video.